Let's talk now about what streams do. We've implied some of the things that it does when we were talking about, for example, the meandering river, and we saw the point bars and the cut banks, but let's talk about it specifically. Streams are agents of surface water transport along Earth's surface, so they move water. They also move sediment. They erode sediment from certain places and they leave it behind, they deposit it in others. They also affect large-scale landscape change. So they are going to create valleys, and they are going to create notches in hills. So we're going to see a little bit about that in here too. We said that streams move water, and we can talk about the amount of water that it moves. And we'll often do so by talking about the volume, which we might say in meters cubed, or we might use something like gallons. Those are each units of volume. And if we're talking about discharge, we want to know how fast it discharges that amount. So we'll talk about it in terms of time, volume per time. So it might be meters cubed per second or gallons per second. Usually streams are large enough that we will use the bigger units here. So in units of cubic meters per second, what is the discharge of this stream down here? The units can be a clue to you of how to calculate this. It's hard to just measure the volume moving past a point, but one thing that you can do is measure the cross-sectional area of the stream. So here we're saying it's roughly a rectangle that's 3 by 10. And so you know what the area is represented by that stream. If you cut through it like cutting through a cake, its cross-sectional area would be 30 square meters. If you also know the speed at which water is moving downstream, or maybe you can place some sort of an instrument in the stream like a rubber duck or a stick, and you can watch how that moves downstream at roughly the same velocity that the water is moving. That can tell you the velocity of the stream. So we have 30 meters squared, and we know that it's moving at 1 meter per second. Using the units, it can clue you in that if you were to multiply these together, you would get units of meters cubed per second, which is discharge. In this particular river, the discharge is 30 cubic meters per second. And we got that from knowing the area and knowing the velocity. So our equation then for calculating discharge, volume per time, is the cross-sectional area times the velocity of the river. Discharge equals area times velocity. You might see it written out in a very simplified way, like this. Q equals A times V. So Q is discharge, A is area, and V is velocity, speed of the water moving. So I've suggested that you can use the velocity of the stream. We already saw when we were talking about meandering streams that they move slower in some parts and faster in others. If you actually look at that cross-sectional view and were to really accurately measure the velocity, you would realize that it varies within a stream profile, within a stream cross-section, which complicates the true calculation. We won't worry about the sort of calculus that you would need to do to calculate that accurately. Instead, we'll just think, okay, what is the average discharge and the average area? And we'll use that. But I do want you to know that if you are looking at the true velocities in a stream, that the center of the stream displaced toward the side where you are eroding is where the water is actually moving the fastest. And toward the channel bottom, right, where it's dragging along the sediment or the rock that's there is where it's actually slowest. River discharge is a big function of the climate in the area that they're draining. So rivers that drain really wet areas are going to have a lot more discharge than areas that drain temperate or drier areas. For example, the Amazon is the river with the largest amount of discharge in the whole world. Its discharge is 209,000 cubic meters per second. It's a huge amount of water moving through the Amazon, and it's doing so not because it's moving particularly fast as a river. Really, the reason that it can move so much water is that it's got such a huge area because it's draining such a huge drainage basin that is, most of the Amazon jungle, rainforest, excuse me. And that area is so wet because it's in the tropics. We'll talk a little bit more later in the course about why that is, but knowing that its drainage area is really tropical, has a lot of rainfall, so a lot of that water ends up running off the land surface and ending up in the Amazon River, contributing to its overall discharge here of 209,000 cubic meters per second. Other rivers that have pretty high amounts of discharge, the Congo and the Orinoco, here are draining the same area. Or excuse me, this one is draining Africa, this one's draining a different part of the Amazon, also tropical areas. In contrast, the Mississippi is puny down here. It's only ranked 15th in terms of discharge. Its discharge is less than 20,000 cubic meters per second. Now, that's still a huge amount of discharge, but it's less than 10 times, or it's less than a tenth that of the Amazon. Amazon is over 10 times more discharge than the Mississippi. And that's really just because most of the drainage area that the Mississippi is actually draining is pretty temperate. It has a decent amount of rain, but not nearly as much as the tropics do. So that's the discharge, that's the water movement. Streams also move sediment, and we break it up into 3 different types of sediment. There's the bed load, the normal bed load. That's material being moved along the bed. It's maybe rolling along, or it's being bounced along, saltating. But it isn't totally suspended in the water. It's still being moved down, but it's being moved down in jumps. Whereas the suspended load are much finer particles. The bed load can move particles of really any size. The suspended load can only move those particles that are the smallest that can stay floating in the water. So that's generally going to be things like clay, maybe some silt, and in particularly fast rivers, you might have some sand in there. But for the most part, suspended load is going to be clay particles. So we got bed load, suspended load, and then one other kind of sediment is dissolved ions, broken up, individual atoms or molecular ions that are charged, that are chemically dissolved in the water. So those are, of course, the smallest out of all of these, because they're often single atoms. Most of the material in a river, most of its sediment is not actually moving during normal course of a river. And much of it only moves during the course of a flood, when there's a lot of water and it's moving fast relative to how fast it normally moves. So the bottom of a river is actually shaped a lot by the floods that happen, and not as much by the normal course of that river. Remember that the bed load tends to be the larger particles, can move tiny particles, but it's the only thing that can move large particles. Suspended load are the smaller particles that can stay suspended or floating in the water. A couple more terms for you to know. There's competence and there's capacity. So competence is a measure of the largest particle that a stream can transport, whereas capacity is the total amount of sediment. Maybe you measure it in terms of mass or total volume, but it's the amount of sediment that a stream can transport, taking into account all the particles that make it up. So competence is largest particle, capacity is the total amount of sediment moved. So take a guess at this one. Thought question here, how would you describe the Mississippi River at the point where it meets the Gulf of Mexico? Here, the Mississippi River is pretty wide. It's moving slow, but it does have a lot of discharge. So what do you think the answer is? It is big, so it can move a lot of sediment. So it's got to be one of these high capacity ones. But The river itself is moving relatively slowly, so most of its load is going to be things like silt and clay, and not as much things like gravel. Because it's not moving fast, it's got low competence. So here's a picture of our Mississippi River Delta, and we can see some of the silt being moved along that delta. The river moving in this direction is over time dumping out all of the sediment that we see all along here. This whole big fan of sediment on either side is what constitutes the delta. Why is all of the sediment dumping out right here as it meets the ocean? Because this water, right, it's slowly moving, but it is moving. And then as it hits the ocean, it really slows down and essentially stops. So that's where the river slows down. That's where it's going to deposit most of its sediment. Narrow mountain streams, in contrast, have high competence. During floods, they can move big cobbles, but they're low capacity. They can't move very much sediment at once because their cross-sectional area here is relatively small, just a few tens or hundreds of square meters. Wide, meandering streams, in contrast, have low competence. The grain size they can move is small, but high capacity. The amount of discharge, and thus the total amount of sediment, is high. So if we're looking at a meandering stream channel here, in between floods, sediments are only going to be deposited and reworked within the channel itself, along the bottom here, right? And you can have some erosion on one side, you'll have some erosion over here, and you'll have some deposition here probably, but it's all taking place within the stream channel. Nothing goes on the floodplain alongside during normal course of the river, in between floods. During a flood, though, most of the time, the water can spread over the floodplain, it can escape the channel because there's so much of it. And when it does so, it's going to drop its sediments along the immediate borders of the channel, forming these levees here. So levees are those natural dams to the river flow that lie along the channel and keep it confined during minor floods. During the major floods, though, the water can leave and actually deposit new sediment on top of those natural levees. The flood itself moves fastest still in the channel. As it breaches, goes over the natural levee, it slows down, and that's why it leaves those layers of sediment on top of the levee during a flood. At that point, it moves very slowly across the landscape, across the floodplain nearby. And because it's moving very slowly, it can even leave behind its finest particles like silt and clay. So your floodplain deposits end up being made of this because the flood is moving so slowly while depositing it. Alluvial fans are a special case that really only forms in dry areas. They are deposited by flash floods coming out of very steep mountain canyons that can carry a lot of big sediment pieces at once, but then they hit this relatively flat valley here, and so, because their slope changes, their speed changes, and they dump out a lot of their sediment all at once, where those steep canyons meet the shallow valley floors. And as a result, they dump these fan shapes. So here's a fan here, right, meeting there, fan shaped, deposits that can have all sorts of particle sizes in them. We've mentioned these before, but I'll go into a little more detail. Terraces are older floodplains which formed when the stream had more water and or sediment, right? So these terraces up here represent old floodplains. Escarpments formed by the erosion of this new river channel into that old terrace, especially during floods, but also, just during the normal course of the river at the cut banks. So if this cut bank continues to move this way, it will erode part of that terrace up there. Here's an example This picture was taken near Yellowstone and the Grand Tetons of the Snake River near Jackson Hole. And you can see this just through the trees here, that there is a river that's moving this way, the Snake River. And so it's got its floodplain that it sometimes covers, but that's way down there. The whole area that's really covered by those trees, that's the floodplain. Then above that, there are layers of those terraces where the deposition used to happen, where the floodplain used to be. A terrace here, then a terrace at a slightly higher elevation here, and then a higher terrace here. And they're connected by steep slopes. These escarpments, an escarpment there, you can just see the lip of it from that side. You can see it better here. And then there's another little escarpment going down to the floodplain now. So we can diagram all those out. We can even see that those same levels are over there across in the distance, where we've got the first terrace, the second terrace, the third terrace that our photographer is standing on, the first, second, and third terrace here. So we can see evidence of some of these in some meandering rivers today. Why did the level of this river and how much it was transporting change so much over time? Well, this area used to be glaciated, and as those glaciers melted, they had a whole lot of water flowing through them. Their discharge was very high. But over time, the discharge and this amount of sediment that this river was moving has decreased over time. So it no longer occupies the highest terrace. Deltas, I've mentioned, and you've probably seen before, but it helps to talk a little bit about exactly what they are. These are depositions of sediment that form where rivers empty into standing water. I've been saying the ocean, but you can also have a delta forming in a lake, or even temporarily when a tributary empties into a very slow moving river. These deltas tend to be made of fine sand and silt, because it's what the meandering river can transport by the time that it reaches the ocean, and then it slows down and dumps that fine sand and silt out in this delta here. Deltas can migrate over time as the river changes course, much like the river channel itself can. And that's actually a major issue in near New Orleans. The course of the Mississippi River naturally wants to change over time. Floods pushing into different channels, avulsion events wanting to escape certain rivers, but we've put a lot of human effort into trying to keep the river from moving. Ancient lobes of the Mississippi River are actually visible if you dig into the sediment around there. It used to follow the course of the Atchafalaya River, and this used to be where its delta was until about 4,000 years before present. Part of it started to move over and it dumped a lot of sediment over here more recently. And then most recently, 3,500 to now, it dumped sediment there. Currently, its delta is actually migrated out into the Mississippi, the Gulf of Mexico there. And so its current sediment deposition is all going on right about here. Without human engineering though, any flood could easily change it and move its location to somewhere totally different in this general area around New Orleans. Here's a satellite picture of what that looks like. You can see some of those old delta lobes and the newest lobe here.